With our last video on lecture 2, basically dealing with our z distributions, assuming our population distribution is normally distributed, we're dealing with Gaussians, and we're working with large sample size. So let's do a couple problems. I'm sure you all have been waiting with bated breath. You worked all your Labor Day weekend and break in order to kind of solve these problems. So let's double check and see that you're on the right path. So marble diameters, once again, bag of marbles. I grab a sample. That's 765 marbles from our population. Population mean is 200 millimeters. Population standard deviation, 20 millimeters. Range of marbles where I can expect to find 60% of the marbles in my population. So we know that one assumption that we're making is that we're normally distributed. No information in the problem statement, but we have to assume that to move forward. N is equal to 765. Oops, let me write that a little bit nicer. 765. So we know that n is greater than 30. So we're greater than or equal to 30. We're dealing with large sample sizes. We know that mu is equal to 200 millimeters. We know that sigma is equal to 20. So we know our z equation is equal to what? X minus mu over sigma. So all that we have to, that's all the information that we're given out right at the outset from our problem. So now the question is asking us what is the range, basically plus or minus x, that is going to give us our value where 60% of our marbles are in our population. So we now need to go to our presentation here, and we're going to go all the way down into our z table. So if I want 30%, I need to find, because again 60%, but z goes from 0 to z, so it's symmetric. So we're looking at something around 0.845, for example. So you can see here, between here and here. So 0.84, 0.85, whichever one you pick, again, it's not going to make that much of a difference. So let's go ahead, and all we have to do now is down here. So we know that our z for 60% is going to be equal to plus or minus 0.845, and now we solve. And when you solve, you'll find that x is going to be equal to either 183.1 millimeters, or these are our bounds, 216.9. And you can double check my math on that, but and the Mathematica notebook has that as well. So, for example, problem done. Let's move on to the next one. So, ultimate tensile strength measurement. Working in a materials company, measure the UTS, ultimate tensile strength. So we know stress versus strain. We know if it's this. For example, this is going to be our ultimate tensile stress, reading off the y-axis here. So we know that mu is equal to 303. Sigma, that's our population mean, population standard deviation. What's the probability of finding a sample that exceeds a UTS of 350? I like this problem because it allows us to draw kind of this distribution. So our mean is 303. So we're centered around the mean. So we're trying to find the probability. So some measure n, 350. So our x equals 350. We want to see what's the probability that our measurement exceeds 350. So we're looking at this area here. So in order to solve for this problem, we know that the total area from our z of equal to 0, so this is equivalent to z equals 0, 0 to infinity, this total area needs to be 0.5. So I want to calculate and figure out what's this area, because once I know this area, I could do 0.5 minus this area, and that's going to give me that area right there. So I need to calculate my z. So z is equal to x, which is 350, minus mu, which is 303, divided by 33. That is going to give me, when I plug that in, give me my value. It's going to be around 0.142. Let me go back and see what that area corresponds to. So 1.42. Let's go to the presentation. Let me make sure. 1.42. Right here. Sometimes you can see kind of like, again, if you wanted an extra project, build that into Mathematica so I don't have to look back constantly at that guy. So 1.42, about 0.422. So this area here is going to be 0.5 minus 0.4222, and that is going to give me, once I multiply that by 100, about 7.78%. That's the probability that I find a measurement or sample that exceeds 350. What were the assumptions I made? Again, assuming for normal and assuming that n was greater than 30 here, which we didn't have. We actually couldn't solve this problem unless we make that assumption. Awesome. So let's go down. Let's do two more problems, and we'll get at it. All right. Let me erase here. So let's draw. Actually, let's draw this guy in black. I like it. Here we go. Probability. Here we go. All right. So measuring voltage in my Helmholtz coil apparatus after 150 exhausting experiments, measurements. Population mean is this, 10 volts. Population standard deviation of 3.4. How many voltage measurements will fall between 10 and 15 volts? So our population mean here, 10 volts. That's our mu. Mu equals that. Sigma is equal to 3.4 volts. We know that n is equal to 150. So we know that n is greater than or equal to 30. So we could do this analysis. We'll also assume that we're normally distributed. So here's my population. So now we're trying to figure out measurements that fall between 10 and 15 volts. So 15V, that's our x value. So we're just looking for this area. So this is a nice problem because it's just plug and chug. So z equals x minus mu divided by sigma. So that is going to give me a value of, once we plug that in, it will give me a z value of 1.47. And it's saying how many voltage measurements, how many measurements will fall between here. So if I go and look at my presentation, that's too bad. Go back down again. Should have clicked 1.47. 1.47. Let's go over here. So 0.4292. So go back. Go back. Let me go scroll down here. So that corresponds to 0.4292. That's my area, the probability, the fraction. I need to multiply by n, my number of experiments, which in this one was 150. Right here. So that's going to give you about 64 measurements. Should fall between 10 and 15. There. All right. Last one. Hopefully, it's just a little bit trivial after this bit. So, but again, we want to make you more and more comfortable. So these are second nature because more difficult problems are coming. Don't worry. If you're bored and it's too easy, I've got plenty more to keep you even in this section of the course. All right. So measuring pressure in a cylindrical pressure vessel. Find that mu is this, sigma is this. Took 120 measurements, so n equals 120. N is greater than or equal to 30. Assume normal. How many measurements will fall between 35 and 45 pascals? So let's write down. So our mu is 39. And we are looking for our sigma is that. So the first question is asking us how many are going to fall between 35 and 45 pascals. So let's draw our distribution. So the first question is asking us to find basically this area. Here, here. So first off, we have to calculate our z's. So our z for the first one is just going to be our 35 minus, excuse me, let me erase that. So our x, which is 35 minus 39, divided by 4. So that is going to give me a z value of -1. Then my other value is going to be 45 minus 39 divided by 4. That's going to give me a z value of 1.5. So this corresponds to an area -1. Let's go look back. I shouldn't have clicked. I'm using my. So -1, which is equivalent to 1, 1.5 here. So 0.3413 plus 0.4332. Let's go back here. So that's going to be the total area here is just going to be this 0.3413 plus 0.4332. That's going to give me an area of 0.7745. That's it. So let's look. Let me erase this guy. That's the first problem. Then it's asking how many are going to be less than 35. So if I want the area here now, less than 35, well, I know that that area was just that 0.3413. So now, if I want the blue area, it's just going to be 0.5 minus 0.3413. And that's going to be equal to approximately 0.1587. And the last problem is how many less than 45? Well, I am now asking for this whole area here. I should switch colors here. I'm looking for this entire area. Well, I know everything to the left of 39 is going to be 0.5. So I know I have to add 0.5 plus what's the area here between 39 and 45? It's just this one that we saw previously. 2 equals, and that's approximately 0.9332. That's it. And again, if it's asking you for how many measurements, all we have to do is multiply these by n. By n, multiply by n, and that's going to give you your value. That's it. That's all you have to deal with for this this section of the course for lecture 2. So next time we're into lecture 3, we're going to talk about central limit theorem, t-samples, t-comparison test, and a lot of other good things. So I'll see you all next time. Thanks. Bye. Have a good one.